Hi everyone, welcome to my talk on Python for statisticians. This is Python version 2, and this is actually a redo of a previous talk that I gave where the sound cut out of the video, and I'm just doing this so I can upload this and you guys can see this with sound. Now, I should say, I am not an expert in Python. I'm just doing this to give you enough information to understand what's going on with the PyCUDA module. The PyCUDA module is a module for Python or an add-on to Python that will make GPU computing a bit easier. You don't have to write as much, you can execute kernels faster, and that's the purpose of my talk. So I'm just going to blow through some things that will help you get started. This is really a substitute for, this is to help you just get started with playing around with some of these things. I'm going to go over a lot of little things today and not really any particular thing in depth. So let's get started. Basic elements. Python is a high-level multi-purpose language and it's interpreted so it's not compiled like C. I say here that it's clumsier than R at number crunching. A bit of the syntax is a bit different. You have to do extra work to load data and format it sometimes, and there's less statistical support natively. I think it's better at string manipulation. It's easier syntactically. It doesn't mean that Python is better than or worse than R inherently. It's just a little bit easier to use for some things, harder to use for other things. So you get this interpreter. If you have Python installed, you can just type in Python, and you're in terminal. If you have a session of bash or TSH or any other shell loaded, you can just type in Python and you get an interpreter. You can use it like a calculator. You can set variables. You can assign them values, and you can do arithmetic on them. You can also write Python scripts. You can take a bit of text, save it in a file, and then call Python on that file. You can type in Python and then give it the file, and it'll execute whatever in this .py file. Single-line hashes are single-line comments, or hashes are single-line comments, rather. You can also use triple quotes as sort of a workaround for multi-line comments. There's no native multi-line comment support, but triple-quoted strings extend over several lines, and this is a good workaround for multi-line comments. You can format strings because every string is an instance of the string class in the object-oriented programming sense. Each string is an object, and it has a bunch of methods attached to it, including this format method. So if you use these curly braces, you can denote fields of a string, and you can call format on them and plug in some values here. You can also use the format function, and you can plug in values printf style, where you have fields like %d, which is a familiar integer field in a printf format string. So I can define my own functions with the def keyword and then call them later with arguments. Notice the indentation here in the if-else block and inside the function definition. Indentation is really important because indentation is used to delineate blocks of code, nested blocks of code. They're like indents are like the curly braces in C. So if I define a function like this, where the return is meant to go under else, but is indented at the same level as else, I'll get an error because return should have been indented by however many spaces I had here or here or here. Indentation's got to be there, and it's got to be consistent. Line continuations with a single slash. Logic and control flow, there's and, double equals, less equal, greater than, there's not, and there's or. They all work in a way that you think they would. Here's an example of an if-else statement. You can check it out. I just store A as something. I give this value to A, and I run the if-else statement, and it works like you think it would. Notice the elif instead of else if for you R users out there. It's not if-else or else if, it's elif. Strings can be specified in a bunch of different ways. There's triple quoting, there's the apostrophe sign, and there's single quoting. And only triple quotes can extend over multiple lines. You can slice strings in this way. You can specify a range of things. You can specify single characters because strings are arrays of characters. If you don't specify anything on one side of the colon, it just runs to the beginning or the end and prints out the corresponding range. If you specify a number at the end, then this is non-inclusive. So this will print element 3 of string A inclusive up to 8 not inclusive. So 0, 1, 2, 3, you get an L first, L-O-W-O-R-L-W-O then. So we have character 0, 1, 2, 3, 4, 5, 6, 7. This O at the end is this character 7, not character 8. So this range does not includes 3, but doesn't include the 8. Type conversion is pretty easy with the int, float, and str functions. You should play around with that if you haven't already. You can concatenate strings really easily with the plus sign. I really like this about Python. I wish that the language R had it. It's really convenient. JavaScript has this, Python has it, and more languages should. Strings are instances of the string class. So you get a bunch of functions like member functions like count and find. You can find length with a function that you can use on its own without having to be built into a string. There's also built-in member functions of the class string, like isAlpha and isAlphaNum. You can check the content of these strings, whether they're all letters or they're all letters and numbers. You can split them into a list of strings by a certain character, or you can join a list of strings together. You can split by lines, which takes care of the new line characters. That's shorthand for split with the new line character right here. Now, I mentioned something called a list here. Lists are a different data type, and they're ordered sequences of objects, each of which can have any type. So this is a list. It's got a couple numbers, it's got a string, and it's got a list inside the list as a member. And you can slice lists. Remember, 0 inclusive, 1 not inclusive. So this slicing only gives us one element. That's the one that comes at the beginning. In this slicing, this is pretty complicated. You take out element 3, which is this list. You take out element 1 of that. And that's this string here, the 3 string. And you take character 1 of that, that's this H here. Remember, indexing starts from 0, not 1. And that's why you get this H out here. You can append things with the append member function. And so this new element just gets added to the end. I can also remove elements with this remove function, but be careful because if this is my list and I call remove C, it won't remove all instances of C, it'll just remove the first one from the beginning. So I'll have to call it twice in this case to remove both instances of the string C. Now tuples. Tuples are a data type that are similar to lists. They can also have members that are of different types. The tuple with only one element has to have this comma right after the first element, so be careful if you want to specify tuples with only one element. You can specify the empty tuple like this. You can get the length of them. There are these tuple comprehension tools that are really neat. You can extract each element of the tuple C. Remember, C was defined up here. You can extract each element and put each element into a different variable with this notation, this assignment. That's what makes tuples a bit convenient. Well, one of the things that make them convenient. You can generate a list of tuples with a zip function. So if I have an array of a list of keys and a list of values, I use the zip function to zip them together, and I get a list of tuples, and each tuple is a key value pair, one from the keys list, one from the values list. But if you want to work with keys and values, I would use dictionaries instead. Dictionaries are this native type that's a collection of key value pairs, and it's a powerful feature of Python. R has it, a similar data type, which is a vector. Dictionaries are kind of like named vectors in R, except that the values can have any data type you want them to have. So here's my dictionary. I can create new elements by specifying new keys and assigning them values. I can create dictionaries out of lists of keys and values by zipping them together first to get a list of tuples, and then calling a dict function on that list of tuples to get a dictionary of key value pairs. Iteration. Moving on. I can create a for loop in many different ways to iterate. I can iterate over all the characters in a string. I can iterate over all elements of a list. I can iterate over all the keys in a dictionary. I'm just speeding through this really quickly here. Here's a list that I can iterate over, and this is the exact same thing as this, iterating over this range object. Range is just shorthand for a list of numbers 0 to, in this case, 9. And this is just a list object. Now, suppose you want to iterate over a list of, over the numbers from 0 to 9,999 times really big number instead of 9 here. Suppose you want to iterate up to really big number. I would not use range here. I'd use xrange. And xrange, unlike range, doesn't take up a lot of memory because it just gives you, because xrange just gives you values on a need-to-know basis. So this will be a lot more memory efficient. It'll go really slowly, but it'll be more memory efficient than range because it doesn't store the list of numbers from 0 to this big thing. It just gives you each number in the each iteration of the loop on a need-to-know basis. It gives you each value of n on a need-to-know basis. Now, xrange, not range, I meant to say xrange here, is a special case of a larger class of functions called generators. And generators are these functions that give you things on a need-to-know basis. So if I specify a countdown here, if I add the word yield, then that's what makes it an iterator. That's what makes the function an iterator. So if I go through this while loop and decrement each value of n by 1, if I have this yield n here, that means return n and store the next value of n for the next call to this function. It's easier to see in an example. So if I have a new countdown object, I call it C, and I call next on it. Next is this function that's common to all iterators. It'll give me the next value, which is 5, and it'll also print this counting down thing because I said to do it here. Each time I call next, it'll print out one value less. A value lower than the last one, rather. Now, list comprehensions are powerful. There's this thing where you can specify lists from other lists with this sort of for loop syntax. So if I have a list of numbers, I can say n times n for n in nums. That just takes all the squares. And you can do similar things too. I can add conditions to them. So if I have this list here called S, and I say S, whoops, S is some different list. Anyway, if I have a list called S, oh, yeah, never mind. So A is my list. A is this list here. S in this syntax is an element of A. And I put that element S in this new list if and only if that number is greater than or equal to 0. So what this does is just extracts all the non-negative elements from A. And in general, you can have this syntax where you have a bunch of, you can specify a bunch of for loop type lines with conditions on them, and you can get a list of things. And in general, you're going to get a list of tuples or scalars. Filter, map, and reduce, along with lambda functions, are ideas in functional programming. You may have seen them in languages like Haskell. And this can be useful sometimes. These ideas, I believe, originated from lambda calculus and category theory, and people decided to build them into computer languages. But it's a lot simpler than that sounds. So all you need to know are lambda functions are the following, basically. Lambda functions are compact ways of writing functions. They're function literals. And there's an example of a lambda function way back, where if you just type in def something, or you type in, oh, yeah. I'll show you an example of a lambda function. Filter just takes a list, picks out all the elements for E for which fun of E is true, and makes a new list out of that. So it filters out a list based on this function. Map applies fun to each element of a list and collects the return values in a new list, basically maps the function to every element of that list. Reduce is like a pairwise sum. It applies this binary operator function, or fun, on this list over and over again until you get a scalar out. So it's just a reduction in the sense that I explained earlier, as like in the pairwise sum, the pairwise product. You give reduce a scalar, you give reduce a vector and a binary operator. It applies that binary operator over and over again until you get a scalar. If fun were addition, then this would be the pairwise sum. This is an idea in object-oriented programming. You'll see this sort of thing in Google's MapReduce and in Hadoop, other tools for massively parallel computing. What they do is they just apply map, then reduce, then map, then reduce over and over and over again. And that turns out to be a very flexible, very powerful idea. So the other thing I didn't specify was how to make a lambda function. You just use the keyword lambda and give it some arguments. On the other side of the colon is an expression giving the return value. And this is neat shorthand because you don't need to use the def keyword to define a function. You can just say filter this, and you can just input this lambda function. That's a function, or you can define a function elsewhere, but sometimes it's just easier to define a lambda function. This lambda is just this true-false condition. It's a function that returns true whenever this argument's greater than 3 and false otherwise. And it just filters out all the elements that are greater than 3, which in this list, in this case, is just 4 and 5. And there are other examples of lambda functions and their usages in filter, map, and reduce that you can play with. File input output. It's similar to C. You create a file handler with the open function. You give a file name or a file path. You give it a code that specifies read or write or append. And in this case, I'm generating a file, so I'm going to write this string to it. f.write just writes a text to that stream or handler. The file that I get is just a data file. Now, this is the sort of data file that R is really good at reading with read.table and read.csv. But for Python, if we wanted to read something like that, we would have to do some extra work. We'd have to create a file handler, we'd have to call readline or readlines to get the data in. And then you would have a list of lines. Each of these lines is text, and I need to parse them. I need to replace the new line characters with empty text, and I can do that with a list comprehension for my actual data. Here we have a list of lines without the new line character. If I call this replace on our data D, or data, sorry, data, which is actually called data, not D. And then for each line, I can split it by field. So I have a list of lists of rows, and I can make each element into a number instead of text, and that completes my parsing here. A lot more work than in R, but still doable. On to modules. Modules are external packages of code. They're not usually built in, but they're there because you don't want to load you don't want the Python's native code to be too bloated. Otherwise, Python would take a long time to load. You only want the support from Python that you actually need at the time, which is why if you want to use the math library or math module, for example, you want to, it doesn't automatically load. The math functions like square root, sine, and cosine don't automatically load with you in each session. If you want to use them, you have to import the math module. And now if you type in math.squareroot, you're going to be able to compute these things. Each module has its own namespace. So math.squareroot in this example works, but just calling square root doesn't, even though math is already loaded. So you can avoid having to type math.squareroot every time by abbreviating the math namespace with some alias. Here it's M. Or you could do something like from math import everything, and then you can just use the square root function. But be careful to avoid conflicts, because there may be another function that you called square root by mistake, and there'd be some sort of conflict there. You can print out where the math module is here. I'm not actually going to go over these two slides and these next couple slides in as much depth. There's this business that we at Iowa State sometimes have with needing to install modules and R packages locally, because we use servers like Impact 1, which have graphics cards on them, CUDA capable graphics cards, and we want to install modules locally because we don't have permission to install them globally for everyone, and we don't want to bother the IT people every time you want to install a package. And so there's these series of steps that I outline here to install a module locally. And I'm not going to go through all of this here. You can read about this on your own. But the main thing to take away from here is when you do your Python setup.py install within the directory of the source files for the module, you need this user flag to make sure that you're installing the package locally. And also you want to make sure that you know where this is installed. And I want to take this directory, this site packages directly, and I want to make sure my shell knows where it is. And I do that by opening my bashrc or my configuration file for TSH by running TSH. But in any case, I want to open my shell's configuration file and tell the shell where Python is, where the Python packages are. So there's this thing called pythonpath, which is where Python's going to look for packages, and I want to add to this path, that's what this colon is, and concatenating to pythonpath, this path to my local packages. And if you don't understand this, I would go read up on shell scripting things like the bash shell, the born again shell, or TSH, or whatever you have on your system. Once those changes take effect, I can load said module to test it. Remember, the import command imports the module, loads the module, and the module name should be in all lowercase letters. Even though SQL Alchemy had some capital letters at the beginning, I need to specify everything in lowercase in order to load that module. There's the sys module, which has system-specific parameters such as argv, which is a list of arguments to the program. So if I call Python in batch mode, where I give it an external file and some other arguments, sys.argv contains all those arguments plus the program name. Now the NumPy module is useful for arrays, matrices. I can make arrays pretty easily with some shortcut functions here. If I import the NumPy module, it gives us the arange function, which specifies a range of numbers and makes an array out of them. This is similar to the range function that you've seen. I can reshape it to give it some number of rows and a number of columns. Transposing does what you think it does. I can give it I can print the dimensions and the size. I have all these shortcut functions like ones and empty, and sum just takes up the sum of the elements. I can do array subtraction. If C equals A minus B, it just takes the element-wise difference. So if I have an array of things A, and I have an array B, I take A minus B, it just takes the element-wise difference. I can also exponentiate things and take trigonometric functions of things. Element-wise, you can have arrays of logical types, arrays of booleans. It's important to distinguish between the element-wise products and the matrix products. So if I say A asterisk B, and A and B are both arrays, it'll take each element, each of the corresponding pairs of elements, and multiply all those pairs together. Multiply the elements of each pair together. So keep in mind, element-wise product versus the dot function, which is the matrix product. You really want to distinguish between those in arrays. Arrays can be sliced and indexed. I can specify the first row or the second row. This gives me rows 0 to 0 inclusive to 2 non-inclusive, so the first couple of rows. If I specify two numbers in brackets separated by a comma, I can get single elements. I can slice by rows and columns at the same time, and that's really convenient for sectioning arrays. And this is just shorthand for get the first row or get the first column, the first column, and you can iterate over arrays. If I iterate over an array just like it is, it's going to iterate over the rows. If I want to iterate over the elements themselves, I should use the flat member of an array, which gives us what you think it is, a flat version of the array in row major order. You can stack arrays. VStack is similar to rbind in C. Takes all the rows of A, puts them on top of the rows of B, and gives me a new array. Here's A, here's B. And hstack is similar to cbind, and this is the return value. Again, speeding through this really fast, but this is where you start looking for familiarity in Python. The default copying in arrays is shallow copying. So .view is also a shallow copy, gives you a shallow copy, or you can just assign C to A, and it does the same thing. And what this does is it passes on a reference of A, not the whole full-blown array itself. So if I pass C a reference to A, and I change a value in A, that also changes the corresponding value in C. So these two things mirror each other because C is really just a reference to A. This is the default behavior. So you got to watch out. If I just say B equals A, and I make a change to A, the same thing is going to happen to B. If I want to deep copy it, if I want to copy all of A to all of B, I got to use this copy function. I should stop saying things like dot copy because copy is really the member function and dot is a way to access members of an object. But this is deep copying. You can have logical arrays just like in R. Here's an array of Boolean types, and this A of B just says, let's take a flat array of elements in A for which the corresponding element in B is true. This is a neat way to subset elements of an array, or to subset data. It's really useful. R makes extensive use of this feature too, so R users should be familiar with this. I rely on it a lot. So, there's also this linear algebra submodule, the NumPy module. It gives you transposes, inverses. Here's a shorthand for the identity matrix with 2 rows and 2 columns. There you can take traces, you can solve linear equations, you can get eigenvalues and eigenvectors, and a description of how to read the output, which is essential. Matrices are a data type that are similar to but distinct from arrays. Matrices are not arrays and vice versa. So here's an example of some usages. You can make a matrix. This way you get this shorthand with string here, semicolons separate lines. That's pretty neat. Arrays have a transpose member. If you're working with, matrices have transpose member. This does not, the T is not a member of an array. It's a member of a matrix, and it is the transpose of whatever matrix you say. The asterisk denotes matrix multiplication, not element-wise multiplication. If A and Y were arrays, this would give you the element-wise product. But since we're working with matrices, it gives you the matrix product. You can take inverses really easily, again, solving systems of linear equations. Indexing and slicing are different. So if A is an array, M is a matrix, this slicing gives you the transpose of column 1 of A, since A is an array. But if you slice at the matrix M the same way, it gives you the same column, only not transposed. There are a lot of other useful modules out there. So there's SciPy, which has a bunch of different scientific computing algorithms. It's kind of like the GSL of Python. It serves a similar purpose. You got Fourier transforms, you got interpolation, optimization, you have a statistical library, you have clustering algorithms, you have library of constants. A lot of neat stuff for scientific computing. There's matplotlib as well, which is for graphics. This has been around for a long time. There's been a lot of great graphics work that's been done in Python. It's built on top of matplotlib, and you should check it out. All of this was to lead us to the PyCUDA module, which is the topic of the next talk, which is a great way for writing and executing GPU kernels from within Python easily. Remember, in CUDA C, there's a lot of overhead to set up the memory and initialize things and copy memory over and copy memory back and free things. You don't have to worry about any of that in Python if you use the PyCUDA module. That's the power of PyCUDA. And stay tuned for that. Well, I guess since this is a repeat video, I should say that it's already online. I blew through a whole bunch of things. This should give you some idea of how a statistician might initially approach Python. This is just to give you some information about what to start playing around with, and you should do the work from there. And the references you can continue with are here. So I mostly drew from an old book by Beasley. He wrote it in 2009. Python's gone a long way since then, so I would check on what's up to date. Here's a link to a NumPy tutorial from scipy.org. Scipy contains NumPy. Here's matplotlib and a scipy tutorial. You'll find an intro to Python code. You'll find this on the website. It's just all the code from today in one big script, and you can run it in Python. And as always, here's the link to the main materials. Thanks for